Okay, Unit 6. Hello. Hi. Hi. Hi, everybody. Hi. I'm talking. Yay. Hello. Unit 6 is on bonding, and this is that fun unit where we draw Lewis dot structures and do shapes and hybridization, which you haven't learned yet, and bond angles and all of that fun stuff. Okay? So today we're just going to talk about the basics of chemical bonding and the different types of bonds. So there's no right or wrong answer to this. What is a chemical bond? Scott? Jacob? Scott? Go ahead. Sharing of valence electrons, potentially, but we have bonds where you know, it's a transfer, but yeah, that's the right idea. Yeah. Like a bond of energy that keeps two electrons together. Electrons. Why do we bond? What's the purpose of bonding? Friendship? Yes. No. To form why? But why do we form compounds? Yeah, these atoms are sharing electrons or transferring electrons or taking electrons because they want to form some sort of stability. They want to get to a lower energy, which usually entails getting a full octet or completing their outer shell. If they're expanded, it could be more than 8. But the purpose of a bond is to become more stable in some way, shape, or form. Okay? Why do atoms bond with each other to form compounds? I just answered that. So let's move on and talk about the 3 main different kinds of bonds. Ionic bonding, electrons are transferred. Covalent bonding, this should be really nonpolar covalent. Specifically when it says electrons are shared equally by nuclei. And then what about intermediate cases? Polar covalent bonding is huge in AP. We got to know a lot about that. We got to be able to draw something called a dipole moment. So what I like to do before is do a little visual here. I'm going to pick on Rui because I threw a ball at his face last time. I got to keep it going. So in this ruler, there's 2 electrons. Okay, Rui and I are going to share these electrons. We have the same electronegativity. Okay, so equal distribution. What kind of bond is this? Non-polar. Okay, no partial charges. We're all good. So now Rui is going to become slightly more electronegative than me, and what's going to happen to these electrons? They're going to get closer to him. So now we have a dipole moment between us. Electrons are more towards him, making him partially negative and me partially positive. When you indicate partial charges, there's no value, no 1, 2, 3. It's just partially negative and partially positive. Okay? And now Rui's going to be like 5 times more electronegative than me. And what is he going to do? He's just going to take them from me. We're not sharing anymore, right? But how do we bond? I'm positive. You're negative Nancy. So positive Paul and negative Nancy are going to electrostatically attract. And don't be perverts. We're just electrostatically attracting. Nothing weird. Okay. So, no, I get to look on the faces. The guys go like snicker, snicker. I'm like, how old are y'all? Y'all are not 12. Okay. So, ionic bonding is an attraction between oppositely charged particles. And then polar covalent is an unequal sharing, and nonpolar covalent is an equal sharing. So when you indicate something's polar, say we have HCl, which one of these likes electrons more? Cl is more electronegative. So you're going to learn more of this on Monday, but you draw an arrow toward the Cl. On tonight's homework, you're going to have to indicate whether or not the partial charges written on a compound are correct. So this would be correct because the negative lies on the chlorine because it's more electronegative. So the electronegative side is the partial. It's a lowercase delta, partial, positive, or negative. Okay? Get used to it. I'm just laughing. We got like people having picnics. We got picnic there. We got someone eating out of a bowl and clinking with a real fork. Like, what's going on today? What's going on with the world? Trump gets elected, and then y'all just go crazy. All right. So, electronegativity then, we already talked about this trend. This is important because it's differences in electronegativity that determine whether the bond's going to be polar, nonpolar, or ionic. Back in the day, we used to do subtraction of electronegativity values to classify things as polar or nonpolar. For instance, if the difference of electronegativity was less than 0.4, we called it nonpolar. And then if the difference was like between 1.6, 0.4 and 1.6, 0.4 and 1.6, we'd call it polar. And anything greater, I always do my thingies wrong. Greater than, that's greater than? No. Is that less than 0.4? No. Okay. That's right, right? Less than 0.4. Anything greater than 1.6 difference would be ionic. We don't do that. The AP doesn't do it. But I want you to know, on tonight's homework, they're going to ask a question like, between boron and hydrogen, what is that? And then I'm telling you just to say it's polar because they're a little bit different, right? So there's going to be more attraction of electrons from one to the other just because they're not the exact same electronegativity. So here, boron is 2.0, hydrogen is 2.1. Who's more attracting electrons? Huh? Hydrogen. Okay, guys, 2.1 is bigger than 2. So hydrogen's going to attract the electrons more than the boron. But because that difference is less than 0.4, in a lot of different categories and classifications, they will say that's really nonpolar. We're not doing that. So on tonight's homework, you'll see the answer. It'll say polar, nonpolar, and you'll be like, why? It's because of this difference thing. So our class rule is going to be, if you're nonpolar, you have to have the same electronegativity, like N2, like F2, like O2. And then anything else we're going to say is polar or ionic. So how do we differentiate between polar and ionic without having numbers? Ionic, if there's a metal and a nonmetal, we're ionic. So if there is a metal present, it is ionic. Two nonmetals together, covalent, just like with the nomenclature. Covalent nomenclature was between nonmetals. We got it? All right. So let's apply this stuff. If lithium and fluorine react, which has more attraction for an electron? Fluorine. Fluorine the floozy, right? Fluorine is your most electronegative element. So the closer it is to fluorine, the more electronegative it is. So fluorine. Why? More electronegative. Do we have to remember why it's more electronegative? Do we remember? We just had a test on it. Why is fluorine more electronegative than lithium? Yep, a higher effective nuclear charge. So it's more attracted to electrons. All right, in a bond between fluorine and iodine, which has more attraction for an electron? Fluorine again. Fluorine, because more electronegative. Now, lithium and fluorine is what kind of bond? That would be ionic because lithium is a metal. Fluorine and iodine is what kind of bond? I need more specific than just covalent. Polar covalent. All right, for this one, we're going to arrange the following bonds from most to least polar. So the further apart they are, the bigger the difference, the more polar. The closer they are, the smaller the difference in electronegativity, the least polar. So try to locate stuff on the periodic table. N to F, O to F, and C to F. That one's easy because F is staying still, right? So which one is the most polar? C to F is the most. And then N to F, and then O to F. I had trouble with those alligators when I was a kid, and I still have trouble. Like, I had to sit there and really think about what I just wrote. It's not natural to me. It's my Achilles heel. All right. You know about the mythological story of Achilles, right? Okay. Good. Good to know. All right. C to F, N to O, or Si to F. Level takes precedence, remember. Level takes precedence. Which one's going to be the biggest? SIF. And then C to F, and then N to O. Okay. And the last one, which one's the highest? ClCl, BCl, or SCl? BCl is the biggest difference. Do you see that, Rui? B is on the, it's way far away. And then your SCl, and then your ClCl, which is actually going to be one of the first nonpolar covalent bonds that we're going to say is nonpolar. That dude, nonpolar. Okay, ionic bonding and lattice energy. So this is going to be a little new for you guys. This is talking specifically about the bonding that occurs between ions. When ions come together and form an ionic bond, energy is released. That doesn't make sense. Think about the opposite. If you want to break a bond, you have to put energy in, right? Yes? So if ions come together, the opposite has to be true. So lattice energy is the energy that actually is released when two ions come together and form an ionic crystal. So y'all have seen sodium chloride, right? Table salt. And you've seen a grain of it, right? Do you think that one grain is just an Na and a Cl? No, it's not. It's a lattice that's formed by the attraction of ions taking some sort of special shape. There's different forms and different crystal types and different number of faces that these crystals will have. That's a different course. But what's important to know is that this whole thing makes a lattice, and that's why we call it lattice energy. Y'all know what a lattice is? The thing like you put in your garden and then the vines grow up it. Yeah, and it looks like a lattice because it's got like that. It's like wood. It's a thing that those of you who sneak out of your house climb up to get back to your bedroom at night. I'm just kidding. Oh, yeah. Oh, Matt's like, yeah, I know what you're talking about. All right. So lattice energy is basically the same as something called Coulomb's law. How many of you have had physics already, the whole course? So you've seen Coulomb's law before, right? You have. If you have had physics in engineering, QQ over R. And basically it's the energy or potential between two charges. Well, this works for us in chemistry because what are our two charges? Our ions. And so it's the same kind of situation. This is in physics it's point charges in space or whatever. So lattice energy, based on Coulomb's law, and I want you to know that. If you see it on the AP and they say Coulomb's law, I don't want you to freak out. I want you to focus on QQ over R. Whenever you talk about lattice energy, whenever you talk about why one bond, ionic bond, is stronger than another, you have to use lattice energy as your argument, or Coulomb's law. QQ are the charges of the two ions. Since we're dealing in AMUs, we don't deal in literal charge. We don't deal in a charge of electron is 1 point blah blah times 10 to the negative blah blah. We have AMUs. So we will be putting in +1 and -1 if it's NaCl. Or if it's NaBr, not NaBr, it's still +1. NaS, we'd be putting in a +1 and a -2. Okay? And R is the radius between the two atoms. And that plays a big part in the strength. How does radius play a part? So let's say I have a ruler, a meter stick. It'd be pretty easy for me to break, right? But as I continue to break it, do you think it gets really hard? You get to a point it's really hard to break. So that's kind of what's going on. If you have two nuclei that are super close to each other, super hard to separate them because the electrons of this guy are so close that they're attracted to that nucleus. And the electrons of this guy are so close they're attracted to that nucleus. And that's really difficult to separate. So that's why the radius is indirectly proportional to the lattice energy. As the radius increases, It gets easier and easier to break because it's less lattice energy. Do we got it? So more charge, more lattice energy. More radius, less lattice energy. And those are the two factors that affect it that you need to know, like this. If I say lattice energy, you should be thinking charge radius, charge radius, charge radius, charge radius. Okay? You're not going to have to do actual calculations for this. We're using +1, -1. We're using our atomic mass unit charges just to see the proportion. We're not using it for a physical energy joule value. That you can save for physics. That's what they do there. So here is just a little chart, nothing too fancy, that shows you that you have a big electronegativity difference. They're ionic compounds, and that's what we call a high ionic character or a low covalent character. Character just being, what's the word I'm looking for? What's another word for character? Help me out. Huh? Nature, something like that. The way it is, okay? We're not talking about like a person's character. Traits, properties, yeah. There's this word that I want to use and I just can't get to it. That's cool. All right. If we have no difference in electronegativity, the bonds are nonpolar covalent, and that's going to be a high covalent character or a low ionic character. So what we're going to do with these, this is going to be a little challenging, we're going to identify the type of bonds, and then we're going to rank them based on from most covalent to most ionic character. So starting with ranking, what is NaCl? Ionic. I'm not starting with ranking, I mean classifying. So if we were to do lattice energy, we'd get +1, -1, and we'll worry about the radius in a minute when we rank. We'll talk about it when we compare. LiH, what is LiH? Ionic. Why do I hear a question mark? Ionic? You shouldn't have an issue. Why is this ionic? There's a metal. Not a hard decision. Ionic. Lattice energy is equal to QQ/R. So again, here we have a +1 and a -1. And we compare A and B, we're going to have to figure out which one's radius is bigger or smaller, which we'll do in a minute. HCl, what is this? This is covalent. HF, covalent. And then BeO. BeO's covalent, really? Why is it ionic? Why are we having trouble with this today? Do y'all understand that that's an ionic substance? Why is it ionic? Because there's got a metal. What is going on? Did y'all, like, not sleep or... You guys are freaking me out. This is supposed to be the easy stuff. Okay, that's ionic. If I was going to calculate the lattice energy, let's get our charges. What do we have? Ooh, +2 and -2. So, man, I'm going to have, depending upon the radius, I'm going to have a pretty big lattice energy there. So that's probably going to be one of the most ionic characters, I would guess. But let's see. So let's start from low. Let's start from covalent. Which one of the two covalents has the least ionic character? Which is the least polar? HCl. Why? No. Okay. Well, H is the same, right? So what do we really need to compare? Fluorine and chlorine's electronegativity. Which one's more electronegative? Fluorine. So because H is the same, the one with the fluorine is going to be more polar than the one with the chlorine. So our least ionic character is C. And then we have D. Are we good so far? All right. Now, let's look at some radii comparisons. LiH versus NaCl. Which one is smaller and which one is bigger? Li and H together versus Na and Cl together. That's easy. Come on. LiH, this is smaller, right? Whoops, smaller. And then NaCl, it's like a full energy, couple energy levels down. This is bigger. So between these two, we're not going to put it in our full ranking just yet, but between these two, where are we? I'm going to go ahead and rank it, and this one we can talk about in a minute. Charge with a bigger radius versus charge with a smaller radius. Which one is the less ionic character? NaCl. That has a smaller number. Because I've got the same charges here, I'm dividing this by a bigger radius, correct? So this is going to be the next ionic, and then the next beyond that, based on these four, would be B. B. Now, where does this one fall? You're not going to have to decide, because BeO looks like it's like in between the radius, so it's oh, it actually does work. Never mind. BeO has a smaller radius than that guy, right? So, and it's pretty close in size to LiH, but this is overwhelming. +2 -2. It's not even a +2 -1 or a +1 -2. It's +2 -2. We got two changes here. So that makes this probably your largest anionic character. Now, you're not going to have to do that kind of guessing on the AP. And the next problem we're going to do, they always keep one thing constant. They're always going to keep either radius the same or charge the same, and you compare the other. So let's take a look at it. What classes of elements typically unite to form compounds that contain ionic bonds? Metals and nonmetals. We also can have metals plus a polyatomic, but you know, those are all nonmetals as well. But we can also have two polyatomics. What's our one and only positive polyatomic? Ammonium, right? So if we have like an ammonium plus another nonmetal or another polyatomic, it's ionic as well, because anytime you have a polyatomic ion, it's an ionic bond. Okay, explain the magnitudes. This is an old AP problem from like the late 80s. Explain the magnitude of these lattice energy in terms of ions and size. So you have to give an explanation for this trend. That's commonly what the AP does. They give you the data, you just have to explain it. So what's the same in all of my cases, in the K and the F, and the KCl, and the KBr, and the Ki? What's going to be the same for lattice energy? The charges are the same in all those cases, correct? So this is a matter of comparing the radii. So why does Kf have the biggest lattice energy? No, no, no. Are you guys seriously okay today? It's charge and radius. If charge is the same, what has to be the determining factor? Radius. So let's talk about the radii of those ions. Fluorine has the largest energy because it has the smallest radius. Gosh, I'm a little worried. And I think Matthew's with it, because he keeps looking at me like we're like looking at each other, shaking our heads like, what's going on? What's going on with these people? All right. I like to, when there's an argument like this, I always like to talk about the lowest and the highest. So I would continue this and say, well, Ki. Is that why y'all? Oh, that's, okay. Kf. This is Ki. Ki has the smallest lattice energy because why? It has the largest radius. All right, so you're going to be doing a ton of this radius comparing and charge comparing. That's what all of lattice energy is about.
Is it just the radius of like the element?
Of both. In these, it's the radius from the nucleus of this atom to the nucleus of the other. Those look like boobs. Let's not do that. So, our atoms are square, and here's our radius. It's the radius from here to here. So, K being same is the same is not the issue. So we're looking at this one getting larger and larger, and then this radius increasing and increasing as we go from here to here. And the bigger the radius, the easier that is to break.
Okay. So like because those atoms are getting like bigger, the radius from the K.
The radius from one nucleus to the other is going to get bigger and bigger and bigger. Because that anion, in this case the anion, is getting bigger and bigger and bigger.
Okay.
Are we clear? All right. So that's it for today. Good job.